Greetings, guys. Welcome to another lecture of us on Module 2. Today we're going to be talking about variation of parameters, which is the second method of solving non-homogeneous differential equations. We've already talked about undetermined coefficients. Now, variation of parameters is a method that uses matrices and determinants to figure out the particular solution. Given a second-order general differential equation, as you could see, a sub 2 of x, y double prime, and so on, we write that in standard form by dividing everything by the leading coefficient. And this particular differential equation then becomes what we need to solve a solution for, or find the solution for. Now, variation of parameters makes the following assumption. It says your particular solution, which was based on guessing for the previous method known as undetermined coefficients, it says your particular solution is going to be the product of two new functions, u1 and u2, as the following: u1 y1 plus u2 y2. And that becomes the fundamental guess for your particular solution, which means all you have to do is find two functions, u1 and u2, such that that will be true. In other words, if I take the appropriate derivatives of this particular function and put it into the differential equation, it will satisfy it. So the objective is, how do we find such u1 and u2 functions that will make that happen? Now, the proof of it is on my PowerPoint, and it's focused on lecture slides 60, 61, and 62. But I'm going to just show you the results and not do the proof necessarily, so you could see how these u's are being calculated. Once you take appropriate derivatives of this particular function and substitute it into the differential equation and do the algebra and try to solve for u1 and u2, your effort leads you to the following system of equations: y1 u1 prime plus y2 u2 prime must equal 0, and y1 prime u1 prime plus y2 prime u2 prime equals f of x. So this becomes your system, which then you could simply see that my u1 prime, if you solve it, will be w1 over w. Well, w is the wronskian, and I'll tell you shortly what w1 is. And u2 prime becomes w2 divided by w, where again w is the wronskians. Now, if you recall, w, which is the wronskian, is the determinant of your fundamental solutions and their derivatives. w1, very simple to remember it, w1 will be, what you will do is you'll keep your second column for w1. So remember it that way, that if it's w1, you have to keep the second column the way it is for your w. And if it's w2, you have to keep the first column. So it's the opposite of the number. So if you're finding w1, keep your second column intact. So y2 and y2 prime, that's the second column. This is the first column, and this is your second column of your determinant. So if you're trying to find w1, keep your second column intact without touching it, and change the first column to 0 and f of x. Now, if this was a 3 by 3, so in other words, you'd have three solutions. It's a third order differential equation. Then you'd have written this as 0, 0, f of x. So all your entries in the first column take a 0 except the last one, depending on the dimension of the matrix. And then obviously your w2 would be, since it's a w2, we're going to keep the first column intact, which is y1 and y1 prime. And then we'll replace the second column with 0 and f of x. And that becomes the solution for your u prime and u1 prime and u2 prime. But remember, you have to find u1 and u2, not u1 prime and u2 prime. So u1 would simply be the integral of u1 prime, and u2 would simply be the integral of u2 prime. And then you'll have your u1 and u2, and then you could write your particular solution. Now, I also want to show you what a 3 by 3 will look like. In other words, if I have a third order differential equation, I'm going to try to keep the questions here up to second and third order, because I mean you could use the wronskian, or we have a 4x4, 5x5, 6x6, but it becomes just unnecessarily complicated and time consuming. And if you guys know how to do a second order, third order, you can pretty much do any kind of a wronskian process. So for a third order differential equation, my wronskian, my u1 prime will be w1 divided by w. My u2 prime will be w2 divided by w. And my u3 prime will be w3 divided by w. Remember that you are guessing a particular solution that looks like u1 y1 plus u2 y2 plus u3 y3, given that you have y1, y2, y3 from the homogeneous part, and those are your fundamental solutions. So to find the particular solution, you basically need to figure out u1, u2, and u3. And how do you figure those out? Well, you do the divisions of the determinants on top, and then you integrate. So, and just one more time so I could write what w would be in a 3x3 scenario. W would be y1, y2, and y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, and y3 double prime. And that will be your wronskian. Your w1 will be, remember, if it's w1, you have to keep the, it's always the opposite of the number, so you have to keep the column 3 and column 2 the same, except the first one. And then the first one takes all zeros except the last one that takes an F. So since it's a 3x3, the first two entries will be 0, the third one will be an F. And for the other two columns, you'll just keep the ones you had on the W. So it'll be y2, y3, y2 prime, y3 prime, y2 double prime, y3 double prime, and this will be your w1. That'll be your w1. So then I need to figure out my w2. So my w2 will be, now this time it's w2, so that means you're going to keep the 1 and 3 constant, I mean the way as it was in the wronskian, and you're going to change the second column to 0, 0, 0, and f of x at the end. So usually it's very simple. You go with the number that you're trying to find. So if it's the first w1, the first wronskian, then the first column takes the zeros and the f of x. If it's w2, then the second column takes the zeros and f of x, and all the other columns stay the same, and maybe that's a better way of remembering it. So it's a w2, the first column stays the same, and if it's a w2, the first column stays the same, the second column changes to zeros and f's, and the third column stays the same. So for w2, we'll have y1, y1 prime, y1 double prime. The second column changes to zeros and f of x, and the third column again stays the same, y3, y3 prime, y3 double prime. And then you can write w3 the same way. It's a w3, so the first two columns will stay the same, y1, y2, y1 prime, y1 double prime, y2 prime, y2 double prime, and the third column changes to zeros and f. And that's how you could find all three w's, and then divide them by the original wronskian, and then find your u's, and then take the integrals, and then you'll have it. Let's look at an actual solution, and again the proof has been detailed step by step very carefully on the PowerPoint. The proof itself is on slides 63, 64, and 65. And the best way to actually show this to you guys now is to actually go ahead and do an example. So the example of differential equation we'll be looking at will be y double prime minus 4y prime plus 4y equal to x plus 1 e to the 2x. Now, let's continue with this. All right, so I have a non-homogeneous differential equation here. So as I've told you earlier, first we solve the homogeneous case independent of whether you're using the undetermined coefficients or variation of parameters. So my homogeneous solution will use a characteristic equation of m squared minus 4m plus 4 equal to 0. This gives me a double root, m minus 2 squared equal to 0, which implies m is equal to 2, and that's a double root. Which means at this point I could very simply write my homogeneous solution. It will be C1e to the 2x plus C plus C2x e to the 2x. So this becomes my y1, this becomes my y2, and those are fundamental solutions. So there's my homogeneous solution for the differential equation, labeled as y sub h. Put a nice red box around this so I won't forget it. So there's my homogeneous solution. Now it's time for me to find my particular solution. Now remember that my particular solution is going to be u1 y1 plus u2 y2, and the objective of using the method of variation of parameters here is to literally find u1 and u2. So again, the objective here is to find u1 and u2. Now if you look at the formula from before, u1 will be the integral of u1 prime, and u1 prime will be w1 divided by w. So if I go back to my problem, then I'm going to be able to find my u1 prime by doing w1 divided by w, and I'm going to find my u2 prime by doing w2 divided by w, and then obviously I will integrate my u primes to find the actual u's. Well, in order to find my u1 prime and u2 prime, I obviously have to find three things. I have to find my w, my Wronskian. My Wronskian will be my functions and their derivatives, my fundamental solutions, that is, from the homogeneous solution and their derivatives. So it will be e to the 2x as my first solution, and x e to the 2x as my second solution. Then the second line will be their derivative, the corresponding derivative. So the derivative of e to the 2x is 2e to the 2x. And the derivative of x e to the 2x, I'm not going to bother with the product rule here, I'll just write the results, will be 2x e to the 2x plus e to the 2x. And if I multiply these two minus the product of these two, you remember how to find the 2 by 2 determinants, you'll get e to the 4x. So I'm going to write that. So there's my w. My w1, again, it's a 2 by 2. So my w1, I'm going to do the first column 0 and f of x. And what's my f of x, guys? You can see it now right on top. It's x plus 1 e to the 2x. So that's going to be my first column. The second column will be unchanged from the original Wronskian, x e to the 2x, and its derivative, 2x e to the 2x plus e to the 2x. So that will be my w1. And finding the determinant of that will be minus quantity x plus 1, x e to the 4x. You could verify that by multiplying these two minus the product of those two. And now I will find w2. So again, the most important part of this work is just the dirty work of finding determinants and derivatives, guys, so it's not that bad. Again, w2, so the second column takes the 0 and the forcing function, which is x plus 1 e to the 2x, and the first column stays untouched from the original Wronskian, which is e to the 2x and 2e to the 2x. Now finding the the determinant of that will yield for my w2, x plus 1 e to the 4x. Fantastic. So now I'm ready to write my u1 prime and u2 prime. So my u1 prime will be w1, which is, there's my w1, which is minus x plus 1 x e to the 4x divided by my actual w, what's my w? It's e to the 4x. And my u2 prime will be my w2, which is x plus 1 e to the 4x. Will be my w2 divided by my wronskian, which is e to the 4x. Now, my u1 prime, if you do the math, it reduces to minus x times x plus 1. And my u2 prime, if you do the math, it will just simply reduces to x plus 1. And at this point, given that u1 will be the integral of these things, and these are all sort of polynomials, and it's very simple to integrate them, which will then allow us to simply derive u1 to be minus 1/3 x cubed minus 1/2 x squared. And same way, my u2 will, if you do simple integration, will be 1/2 x squared plus x, and you need not worry about constants at this point. So therefore, my y particular now, since I have my u1, u2, y1, and y2, I could just write my particular solution right now all together. Will be 1/3 x cubed minus 1/2 x squared, and I have to multiply that by my first fundamental solution, which is e to the 2x. I'm going to scroll up for you to see my first fundamental solution. There is my first fundamental solution in a homogeneous box. That's my second fundamental solution in my homogeneous box. So if I go back down to where I'm writing the solution, it will be y particular u1, y1 plus u2, which is 1/2 x squared plus x, times y2, which is x e to the 2x. And that becomes my fundamental particular solution. And if I clean it all up, my particular solution will be 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. And now I'm ready to write my general solution using the superposition principle, which is the homogeneous solution plus the particular solution. My homogeneous solution is c1 e to the 2x plus c2 x e to the 2x plus my particular solution, which is 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. And now I'm ready to box my final answer. So this becomes my general solution for this second order differential equation. Now there are a few more examples that you guys could follow, several examples actually on this section with all the answers provided for you guys. So good luck, and I will see you guys on the next lecture.